far across the universe, scattered among the stars, exist objects so powerful that they challenge the limits of physics itself. They are born from the violent deaths of massive stars, the catastrophic explosions known as supernovae. When these stars collapse, their cores are crushed into incredibly dense remnants called neutron stars, objects so compact that a single teaspoon of their material would weigh billions of tons. But among these already extreme cosmic bodies, there exists an even stranger and far more dangerous class of star. These are magnetars. Magnetars are the most magnetic objects ever discovered in the universe. Their magnetic fields are so powerful that they can distort the very structure of atoms. If one were to pass halfway between the Earth and the Moon, its magnetic field could wipe out every electronic device on our planet and tear apart the molecules in our bodies. They are rare, violent, and unimaginably powerful. Magnetars unleash bursts of energy so intense that they can briefly outshine entire galaxies. In a single fraction of a second, they release more energy than our sun produces in hundreds of thousands of years. And yet, despite their incredible power, magnetars are incredibly small, only about 20 kilometers wide, a star the size of a city, containing more mass than our sun. But the true mystery of magnetars lies not only in their strength, but in their unpredictability. Because these cosmic objects do not shine peacefully like ordinary stars. They erupt, they crack, and when they do, the entire universe can feel it. Tonight, we explore one of the most terrifying phenomena in the cosmos, the strange physics, the catastrophic eruptions, and the extraordinary magnetic forces of the most dangerous stars in the universe, magnetars. Far out in the vast darkness of space, stars are born, live their lives, and eventually die. Most stars fade quietly, slowly cooling over billions of years. But some stars end their lives in an explosion so powerful that it briefly outshines an entire galaxy. These are the deaths of massive stars. Stars far larger than our sun burn their fuel at an incredible rate. Deep inside their cores, nuclear reactions fuse lighter elements into heavier ones, releasing enormous amounts of energy. This energy pushes outward against the crushing force of gravity, trying to collapse the star inward. For millions of years, the star exists in a delicate balance. Gravity pulls inward. Energy from nuclear fusion pushes outward. As long as this balance continues, the star remains stable. But nothing in the universe lasts forever. Eventually, the star begins to run out of fuel, and when that happens, the balance breaks. The final fuel. In stars like our sun, hydrogen slowly fuses into helium over billions of years, but in massive stars, the process happens far faster and far more violently. After hydrogen is exhausted, the star begins fusing helium, then carbon, then neon, then oxygen, and finally, silicon. Each stage happens faster than the last. The star is desperately trying to maintain the pressure needed to resist gravity. But there is one element that changes everything: iron. Iron cannot release energy through fusion. Instead of producing energy, iron consumes it. When a star begins producing iron in its core, the nuclear engine that supported it for millions of years suddenly shuts down. Without energy pushing outward, gravity takes over, and the collapse begins. The collapse. The core of the star collapses inward at unimaginable speed. In less than a second, the core shrinks dramatically. Matter that once filled a region larger than Earth is crushed into a sphere only a few tens of kilometers across. The atoms inside the core cannot survive this pressure. Electrons are forced into protons, forming neutrons. The result is a new kind of matter, neutron degenerate matter. The collapsing core becomes what astronomers call a neutron star. Meanwhile, the outer layers of the star continue falling inward until they smash into this newly formed neutron core. When they do, something extraordinary happens. The infalling material rebounds outward in a titanic explosion, a supernova. The supernova explosion. Supernova explosions are among the most powerful events in the universe. For a brief moment, the dying star can shine brighter than an entire galaxy of billions of stars. Shockwaves race outward at incredible speeds. Heavy elements forged in the star's interior are blasted into space. Gold, platinum, uranium. Many of the elements found on Earth were created in explosions like these billions of years ago. Supernovae are not only endings, they are also beginnings. They spread the building blocks of planets, oceans, and life across the galaxy. But hidden within the aftermath of these explosions lies something even stranger, something incredibly small, incredibly dense, and incredibly powerful. The birth of a neutron star. At the center of the supernova explosion, the collapsed core remains behind. This object is the neutron star. Neutron stars are among the strangest objects in existence. Despite containing more mass than our Sun, they are only about 20 kilometers across. To imagine this, picture compressing the entire Sun into a sphere roughly the size of a city. The result would be a neutron star. The density is almost impossible to comprehend. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. Gravity on the surface of a neutron star is so strong that if you dropped an object from a height of just 1 meter, it would hit the surface at millions of kilometers per hour. But gravity is not the only extreme property of these objects. Neutron stars also spin incredibly fast. Spinning faster than imagination. When the core of the star collapses, its rotation speeds up dramatically. This happens because of a physical principle called conservation of angular momentum. Imagine an ice skater spinning with their arms extended. When they pull their arms inward, they spin faster. The collapsing star behaves the same way. As its radius shrinks, its rotation speeds up. Some neutron stars rotate hundreds of times per second. These rapidly spinning neutron stars are known as pulsars because they emit beams of radiation that sweep through space like cosmic lighthouses. Every time the beam crosses Earth, we detect a pulse of radiation. These pulses can be incredibly precise, sometimes more accurate than atomic clocks. But not all neutron stars become pulsars. Some evolve into something even more extreme, something far more powerful. The magnetic power of a star's stars already possess magnetic fields during their normal lifetimes. But when a massive star collapses into a neutron star, its magnetic field becomes compressed along with the rest of the star. And when magnetic fields are compressed, they become stronger, much stronger. The magnetic field of Earth is relatively weak. It protects our planet from harmful solar radiation. A refrigerator magnet is already thousands of times stronger than Earth's magnetic field. But the magnetic field of a neutron star is trillions of times stronger. Even this staggering strength is not the limit, because under certain conditions, a neutron star can develop a magnetic field so powerful that it becomes something entirely different. A new kind of cosmic object. The birth of a magnetar. In extremely rare cases, the newborn neutron star spins so rapidly and generates such powerful magnetic forces that its magnetic field grows to unimaginable strength. These neutron stars become magnetars. Magnetars possess the most powerful magnetic fields ever discovered in the universe. Their magnetic fields can reach strengths of 10 to the 15th power gas. To put this into perspective, that is about 1 trillion times stronger than Earth's magnetic field. If a magnetar were located halfway between Earth and the Moon, its magnetic field could destroy every electronic device on our planet. At closer distances, it would tear apart atoms themselves. Even the structure of matter begins to break down under such extreme magnetic forces. But magnetars are not only powerful, they are unstable. Their immense magnetic energy slowly twists and stresses the crust of the neutron star. And eventually, those stresses become too great. The crust cracks. And when that happens, the universe experiences one of the most violent events known to science. But that story belongs to the next chapter of our journey, because magnetars are not quiet stars. They erupt, they fracture, and when they do, their energy can ripple across the galaxy itself. Long before a magnetar begins unleashing its violent magnetic storms across the galaxy, its story begins inside one of the most massive stars in the universe. These stars are giants, cosmic furnaces dozens of times more massive than our Sun, burning their nuclear fuel at extraordinary rates. For millions of years, they shine brilliantly, fusing hydrogen into helium, then heavier and heavier elements inside their cores. But massive stars live fast and die young. Eventually, the delicate balance between gravity and nuclear pressure collapses. Inside the core of a massive star, fusion gradually produces heavier elements: carbon, oxygen, silicon, and finally iron. Iron is the end of the road for nuclear fusion. Unlike lighter elements, fusing iron does not release energy. Instead, it consumes energy. Once the star's core becomes dominated by iron, the furnace begins to fail. The outward pressure that once supported the star against gravity weakens. Then gravity takes over. The core collapses inward at unimaginable speed. In less than a second, matter that once filled a region larger than Earth is crushed into a sphere only about 20 kilometers across. Electrons are forced into protons, creating neutrons and releasing a flood of neutrinos. What remains is a neutron star, a dense remnant where matter is packed so tightly that a single teaspoon would weigh billions of tons. But under certain extremely rare conditions, something even more extraordinary forms: a magnetar. For a neutron star to become a magnetar, two things must happen during its birth. It must spin extremely fast, and its magnetic field must amplify to unimaginable strength. At the moment of collapse, the core of the dying star can begin rotating hundreds of times per second. Conservation of angular momentum, the same principle that makes a spinning ice skater rotate faster when pulling in their arms, causes the collapsing core to spin faster and faster as it shrinks. What was once a slowly rotating stellar core suddenly becomes a compact object spinning dozens or even hundreds of times every second. Inside this newborn neutron star, conditions are so extreme that magnetic fields can be violently amplified. This process is known as the dynamo mechanism. In a newborn neutron star rotating extremely rapidly, swirling motions of electrically charged plasma generate intense magnetic fields. Similar processes occur inside Earth and the Sun, but the magnetar version is far more powerful. Instead of producing magnetic fields of a few Gauss or a few thousand Gauss, the magnetar dynamo can generate fields reaching 10 to the 15th power Gauss. That is a quadrillion times stronger than Earth's magnetic field. At this level of intensity, magnetism becomes one of the dominant forces shaping the star's behavior. The magnetic field threads through the neutron star's crust and extends far into space, forming a complex structure known as the magnetosphere. In normal neutron stars, the magnetosphere channels charged particles along magnetic field lines, creating pulsars, stars that emit beams of radiation like cosmic lighthouses. But magnetars behave differently. Their magnetic fields are so strong that they begin to twist and distort the very crust of the star. Imagine the neutron star's surface as a rigid crystalline shell, only about 1 kilometer thick. Beneath it lies an ocean of superfluid neutrons, matter in a quantum state, unlike anything on Earth. The magnetar's immense magnetic field constantly pulls and twists the crust, building enormous stresses deep within the star. Eventually, the crust can no longer withstand the pressure. It cracks. These cracks are known as starquakes. When a starquake occurs, the magnetar's magnetic field suddenly rearranges itself, releasing colossal bursts of energy into space. These eruptions can produce intense flashes of gamma rays, among the most energetic forms of radiation in the universe. For a few brief moments, a magnetar flare can release more energy than our sun produces in hundreds of thousands of years. And yet, these explosions originate from an object only 20 kilometers wide. Understanding magnetars requires us to rethink the limits of physics. At their surfaces, gravity is so intense that escaping requires speeds approaching half the speed of light. Matter behaves in strange ways. Atomic structures are crushed. Quantum effects dominate. Even light itself can behave differently. In normal conditions, light waves pass through space without interacting with each other. But inside the extreme magnetic environment of a magnetar, the rules change. The magnetic field becomes strong enough to influence the vacuum of space itself, creating an effect known as vacuum birefringence. In this phenomenon, empty space behaves like a crystal, splitting light into different polarizations. This strange effect was predicted by quantum electrodynamics decades ago, but magnetars may be one of the few places in the universe where it can actually occur. The birth of a magnetar is also incredibly rare. Not every massive star creates one. Most stellar collapses produce ordinary neutron stars or black holes. For a magnetar to form, the conditions during the supernova explosion must be just right. Rapid rotation, powerful turbulence, and a strong dynamo effect within the newborn neutron star. Astronomers estimate that only about 10% of neutron stars become magnetars. Even so, the Milky Way likely contains dozens of them. Some are still hidden, waiting to be discovered. Others announce their presence dramatically through bursts of gamma rays detected by orbiting observatories. In fact, magnetars were first discovered not through visible light telescopes, but through space-based detectors designed to observe gamma-ray bursts. One of the earliest clues came in the late 20th century, when astronomers began noticing mysterious flashes of gamma radiation coming from within our galaxy. These bursts were short but incredibly powerful, lasting only fractions of a second, but releasing vast amounts of energy. Initially, scientists were unsure what caused them. Eventually, the evidence pointed toward a new class of object, soft gamma repeaters, or SGRs. Unlike distant gamma-ray bursts caused by collapsing stars or merging neutron stars in distant galaxies, these events were repeating sources located within the Milky Way. Something nearby was periodically unleashing bursts of high-energy radiation. Further observations revealed that these sources were neutron stars with extraordinarily strong magnetic fields, magnetars. Today, astronomers know of several confirmed magnetars scattered across our galaxy. Many lie hidden within supernova remnants, the expanding clouds of debris left behind after the death of massive stars. Others appear isolated, drifting through space long after the remnants of their parent explosions have faded. Despite their rarity, magnetars play an important role in shaping the high-energy environment of the universe. Their eruptions inject energy into surrounding space, influencing nearby gas clouds and accelerating particles to extreme energies. And sometimes, their flares can be detected across vast cosmic distances. One of the most dramatic magnetar eruptions ever observed occurred in December 2004, when a magnetar known as SGR 1806-20 unleashed the most powerful flare ever recorded from our galaxy. The burst was so intense that it briefly affected Earth's upper atmosphere, even though the star lies about 50,000 light-years away. For a fraction of a second, detectors across the solar system were overwhelmed by the surge of gamma rays. If such an eruption occurred closer to Earth, say within a few thousand light-years, the effects could potentially be much more severe. But fortunately, the known magnetars in our region of the galaxy appear to be safely distant. Still, these events remind us that magnetars are not quiet cosmic relics. They are dynamic, unstable, and incredibly powerful, and their birth, through the collapse of massive stars, creates some of the most extreme objects the universe has ever produced. Yet the story of magnetars does not end with their creation. Because once a magnetar exists, its magnetic field continues to evolve, twisting, cracking, erupting. In the next part, we will explore what happens when these unstable magnetic fields unleash their full fury, producing cosmic explosions powerful enough to briefly outshine entire galaxies. The eruptions of magnetars are among the most violent events known in astrophysics, and they can happen without warning. In the silent darkness of space, magnetars rarely remain calm. Their immense magnetic fields are not stable structures. They twist, stretch, and coil like gigantic cosmic springs under extreme tension. Deep within these stars, forces are constantly building, slowly storing energy that can only be released through violent eruptions. When that energy finally escapes, the result is one of the most powerful explosions in the universe. These events are known as magnetar flares. Unlike supernovae, which destroy entire stars. Magnetar flares occur on the surface of the neutron star itself. Yet despite their smaller scale, the energy they release is staggering. In just a fraction of a second, a magnetar can unleash as much energy as our sun produces over hundreds of thousands of years. To understand why these eruptions happen, we must look at the structure of the magnetar itself. A magnetar is essentially a neutron star with an incredibly strong magnetic field embedded throughout its interior. This field threads through the star's crust, twists through the magnetosphere surrounding it, and extends thousands of kilometers into space. But this magnetic field is not static. Over time, it evolves and becomes tangled. Imagine twisting a rubber band tighter and tighter. Eventually, the tension becomes too great, and the rubber band snaps. Inside a magnetar, something very similar happens. The magnetic field lines become distorted and twisted by motions inside the star's ultra-dense interior. These distortions place enormous stresses on the magnetar's crust, a solid shell made of ultra-compressed nuclear matter. Although this crust is incredibly strong, it is not infinitely flexible. Eventually, the pressure becomes too much. The crust fractures. When this happens, the magnetar experiences what scientists call a starquake. A starquake is similar to an earthquake on Earth, but vastly more powerful. The crust suddenly shifts, allowing the twisted magnetic field to rearrange itself violently. As the field snaps into a new configuration, enormous amounts of energy are released. This energy blasts outward in the form of gamma rays, X-rays, and high-energy particles. For a brief moment, the magnetar becomes one of the brightest objects in the galaxy. Astronomers categorize these eruptions into three main types: short bursts, intermediate flares, and giant flares. Short bursts are the most common. They last only a fraction of a second and release energy comparable to what the sun emits in several days. Though impressive, these events are relatively minor compared to what magnetars are capable of. Intermediate flares are rarer and far more powerful. They can last several seconds and release enormous amounts of energy, sometimes equivalent to years of solar output. But the most dramatic events are the giant flares. These are among the most powerful explosions ever recorded within our galaxy. During a giant flare, a magnetar can release 10 to the power of 46 ergs of energy in just a few tenths of a second. That is equivalent to what the sun emits over hundreds of thousands of years, compressed into a single flash of radiation. The energy travels outward at the speed of light, forming a blast wave of gamma rays that spreads through the galaxy. Fortunately, these events are extremely rare. In fact, only a few giant flares have ever been directly observed. The first confirmed giant flare was detected in 1979, when satellites monitoring nuclear test activity suddenly recorded an enormous burst of gamma radiation. At first, scientists feared the signal might indicate a secret nuclear explosion somewhere on Earth, but the signal did not originate from Earth. It came from deep space, from a magnetar located in the Large Magellanic Cloud, a nearby satellite galaxy of the Milky Way. This discovery marked the first clear evidence that neutron stars could produce sudden, massive bursts of gamma radiation. Later observations confirmed the phenomenon. Another giant flare occurred in 1998, when a magnetar known as SGR 1900 plus 14 erupted with incredible intensity. The event flooded detectors with gamma rays and briefly illuminated the surrounding region of space. But the most powerful magnetar flare ever recorded occurred in December 2004. On that day, a magnetar named SGR 1806-2 unleashed a blast so powerful that it was detected by nearly every gamma ray observatory in space. The initial flash lasted only about 0.2 seconds, but it was so intense that it temporarily blinded several satellites designed to observe gamma ray bursts. Even more astonishing, the radiation from the flare actually affected Earth's upper atmosphere. For a brief moment, the burst ionized parts of the ionosphere, the layer of charged particles high above our planet. The magnetar responsible for this eruption lies about 50,000 light-years away, near the center of the Milky Way. Yet even from that immense distance, its explosion had measurable effects here on Earth. To put this into perspective, if such a flare occurred within 10 light-years of Earth, the consequences could be severe. The intense radiation might damage satellites, disrupt communications, and potentially strip away parts of our planet's ozone layer. Fortunately, no known magnetars exist that close to our solar system. Most are located thousands or tens of thousands of light-years away, safely distant from Earth. But magnetar flares do more than simply release radiation. They also reshape the magnetosphere surrounding the star. During a flare, powerful magnetic disturbances ripple outward through space, accelerating particles to nearly the speed of light. These particles spiral along magnetic field lines and produce intense emissions of X-rays and radio waves. Sometimes, these disturbances can even produce mysterious signals known as fast radio bursts, or FRBs. Fast radio bursts are extremely brief flashes of radio energy that last only milliseconds, but release tremendous amounts of power. For years, astronomers debated their origins. Many FRBs appear to come from distant galaxies, but in 2020, scientists detected one originating from a magnetar within the Milky Way. This discovery strongly suggests that magnetars may be responsible for at least some of these mysterious signals. It also revealed that magnetars are not just violent objects. They are also important cosmic laboratories. By studying magnetar eruptions, scientists can explore some of the most extreme physics in the universe. The immense magnetic fields surrounding these stars push the limits of known physical laws. Quantum effects that are normally invisible become observable. Even the vacuum of space behaves differently in such intense environments. Light can change polarization. Particles can spontaneously appear. And magnetic energy can transform into radiation with astonishing efficiency. But magnetars cannot sustain these eruptions forever. Over time, their magnetic fields slowly decay. As the field weakens, the stresses inside the star gradually diminish. The magnetar enters a quieter phase, producing fewer bursts and less intense radiation. Eventually, after tens of thousands of years, the once powerful magnetar becomes indistinguishable from an ordinary neutron star. Its most violent days are over. Yet during its active lifetime, a magnetar leaves a powerful imprint on the surrounding cosmos. Its flares heat nearby gas clouds. Its radiation alters the chemistry of interstellar space. its magnetic disturbances accelerate cosmic particles across vast distances. Even in death, the magnetar continues influencing the galaxy around it. But there is still something even stranger about these stars. Because magnetars are not merely powerful, they are also deeply mysterious. Their magnetic fields may reach strengths where the laws of physics themselves begin to behave in unfamiliar ways. And in the next part of our journey, we will explore how magnetars push the boundaries of quantum physics, revealing phenomena that cannot be recreated anywhere on Earth. In these extreme environments, the universe begins to show us what matter and energy truly look like at their absolute limits. In most places across the universe, the laws of physics behave predictably. Gravity pulls matter together, atoms interact through electromagnetic forces, and light travels through empty space unaffected by its surroundings. But near a magnetar, these familiar rules begin to change. Magnetars exist in a regime of physics so extreme that phenomena predicted only by advanced theories begin to appear in reality. Their magnetic fields are not merely strong, they are so powerful that they begin to influence the very fabric of space itself. To understand just how extreme magnetars are, we need to consider the strength of their magnetic fields. Earth's magnetic field, which guides compasses and protects our atmosphere from solar wind, measures about 0.5 Gauss. A refrigerator magnet is roughly 100 Gauss. The strongest steady magnetic fields created in laboratories on Earth reach about 100,000 Gauss. But a magnetar's magnetic field can exceed 1 quadrillion Gauss. That is 1 quadrillion Gauss. At this level, magnetism becomes the dominant force controlling matter. Atoms behave differently. Electrons are forced into narrow quantum states aligned with magnetic field lines. Chemical bonds become distorted. The very structure of matter is reshaped by magnetism. If a human could somehow approach within a few thousand kilometers of a magnetar, the magnetic field alone would begin pulling apart the atoms in their body. But the most fascinating effects occur not in matter, but in the vacuum of space itself. In everyday life, we think of empty space as exactly that, empty. A vacuum contains nothing, no particles, no substance, no structure. Light passes through it freely without interference. Yet quantum physics tells us that even empty space is not truly empty. Instead, the vacuum is filled with fleeting pairs of virtual particles, tiny fluctuations of energy that appear and disappear almost instantly. Normally, these fluctuations are far too small to observe. But near a magnetar, the magnetic field becomes strong enough to influence them. This leads to one of the strangest predicted phenomena in modern physics: vacuum birefringence. In certain crystals on Earth, light passing through the material splits into two separate beams with different polarizations. This happens because the crystal structure affects how light waves travel through it. Near a magnetar, something similar may happen, except the crystal is not made of matter. It is the vacuum of space itself. The magnetar's magnetic field alters the behavior of virtual particles in the vacuum, effectively turning empty space into a medium that affects how light propagates. Photons traveling through this region may split into different polarizations depending on their orientation relative to the magnetic field. In other words, space itself becomes polarized. This phenomenon was predicted decades ago by quantum electrodynamics, the theory describing how light and matter interact. However, the effect is far too weak to detect in normal environments. Only near objects like magnetars does the magnetic field become strong enough for the effect to be observable. In 2016, astronomers studying a magnetar known as RxJ 185.5-3754 observed unusual polarization patterns in its light, patterns that may be evidence of vacuum birefringence. If confirmed, this observation would represent one of the most dramatic validations of quantum physics ever observed in nature. But magnetars do not stop at bending the rules of light. Their magnetic fields may also influence the structure of atomic nuclei themselves. In normal conditions, atomic nuclei are bound together by the strong nuclear force. But under extremely strong magnetic fields, the balance between electromagnetic forces and nuclear forces can shift. Some theoretical models suggest that near a magnetar's surface, atoms may become elongated into cylindrical shapes, stretched along magnetic field lines like tiny strands of spaghetti. This strange state of matter has sometimes been referred to as nuclear pasta. Although similar structures are predicted inside neutron stars due to extreme pressure, magnetars may produce even more unusual atomic configurations due to their magnetic dominance. These exotic states of matter challenge our understanding of how particles behave under extreme conditions. But perhaps the most extraordinary aspect of magnetars lies beneath their surface. Inside a neutron star, matter exists at densities so high that atomic nuclei are crushed together into a continuous sea of neutrons. These neutrons may form a superfluid, a strange quantum state where matter flows without friction. In this superfluid interior, vortices of spinning neutron matter can form as the star rotates. These vortices help distribute angular momentum throughout the star, maintaining its rotation. But the magnetar's intense magnetic field can interact with these vortices in complex ways. As magnetic stresses build within the crust, they may disturb the internal superfluid layers. This interaction can cause sudden changes in the star's rotation speed, a phenomenon known as a glitch. When a glitch occurs, the magnetar may suddenly spin slightly faster. These events are extremely small changes, often only fractions of a percent, but they provide valuable clues about the internal structure of neutron stars. By studying glitches, astronomers can probe the hidden interior of these objects, revealing information about matter at densities impossible to replicate on Earth. Magnetars also challenge our understanding of how stars evolve over time. Unlike typical neutron stars, whose radiation comes primarily from rotational energy, magnetars shine due to the decay of their magnetic fields. As the magnetic field slowly weakens over thousands of years, it releases energy that heats the star's surface and powers its X-ray emissions. This process makes magnetars some of the brightest neutron stars in the X-ray sky. Yet despite their brightness, they are relatively short-lived in astronomical terms. Over tens of thousands of years, their magnetic fields gradually decay and their violent activity fades. Eventually, the magnetar settles into a quieter state, becoming indistinguishable from an ordinary neutron star. But during their active phase, magnetars represent one of the most extreme environments in the cosmos. They allow scientists to observe physical processes that cannot occur anywhere else. Quantum effects become visible. Magnetic energy dominates over gravity, and matter itself behaves in unfamiliar ways. These stars serve as natural laboratories for testing the deepest theories of physics, from quantum mechanics to general relativity. But magnetars may also influence phenomena far beyond their own immediate surroundings. Some researchers believe that magnetars could be responsible for mysterious cosmic signals detected across the universe, signals that travel billions of light years before reaching Earth. These signals are brief, powerful, and still largely unexplained. They are known as fast radio bursts. And in the next part of our journey, we will explore the possibility that magnetars may be the hidden engines behind these cosmic flashes, revealing a connection between the most dangerous stars in the universe and some of the most mysterious signals ever detected by astronomers. For decades, astronomers believed magnetars were violent, but mostly local phenomena. Rare neutron stars scattered across galaxies, occasionally releasing bursts of radiation that briefly lit up the surrounding cosmos. But in the early 2000s, astronomers began detecting something even stranger: short flashes of radio waves. These signals lasted only a few milliseconds, thousandths of a second. But during that tiny moment, they released enormous amounts of energy. In fact, some of these flashes produced as much energy in a millisecond as the sun emits in several days. At first, scientists had no idea what they were. They became known as fast radio bursts, or FRBs. The first FRB was discovered in 2007 while astronomers were analyzing archival data from the Parkes Radio Telescope in Australia. The signal appeared as a sudden spike in radio frequency energy, lasting just a fraction of a second before disappearing forever. At first, many scientists assumed it was an instrumental error or interference from Earth-based technology. But over time, more bursts were detected. Different telescopes, different observatories, different parts of the sky. The signals were real, and they were coming from space. As astronomers studied these bursts more carefully, they discovered something extraordinary. The radio signals appeared dispersed, spread out across different frequencies in a way that suggested they had traveled through enormous distances of intergalactic space. Lower frequency radio waves arrived slightly later than higher frequencies, a delay caused by electrons scattered throughout the universe. By measuring this delay, astronomers could estimate how far the signal had traveled. The results were astonishing. Many fast radio bursts originated billions of light years away. That meant their sources were incredibly powerful. To produce a detectable signal across such vast distances, whatever generated these bursts must release extraordinary amounts of energy. But what could do that? For years, scientists proposed many possibilities. Some suggested merging neutron stars. Others proposed collapsing black holes. Some even speculated about advanced extraterrestrial civilizations, though most astronomers considered that explanation unlikely. Then a new possibility emerged: magnetars. Magnetars already possessed several characteristics that made them ideal candidates for producing fast radio bursts. They were incredibly energetic, capable of releasing enormous bursts of electromagnetic radiation in very short periods of time. Their magnetic fields could twist, snap, and rearrange violently, exactly the kind of process that could generate intense radio emissions. But until recently, there was no direct proof connecting magnetars to FRBs. That changed in April 2020. On that day, telescopes around the world detected a powerful radio burst coming from within our own galaxy. The signal was far weaker than the distant extragalactic bursts astronomers had observed before, but that was only because the source was relatively nearby. The burst came from a known magnetar called SGR 1935 plus 2154, located about 30,000 light-years away. For the first time, scientists had observed a fast radio burst originating from a magnetar. This discovery provided the strongest evidence yet that magnetars could produce at least some FRBs. But how exactly do magnetars generate these bursts? One leading theory involves the violent rearrangement of magnetic fields during magnetar flares. As the magnetic field twists and snaps, enormous currents of charged particles surge through the magnetosphere surrounding the star. These particles move at nearly the speed of light, interacting with the magnetic field and producing intense radio emissions. Because the magnetic field structure is extremely complex, these emissions can become focused into narrow beams. When one of these beams briefly sweeps across Earth, astronomers detect it as a fast radio burst. But magnetars may produce FRBs through another mechanism as well. During powerful magnetar flares, shockwaves of energy propagate outward through the surrounding plasma. These shockwaves can accelerate electrons and produce bursts of radio waves through a process known as synchrotron maser emission. In this scenario, the radio burst is produced not directly by the magnetar itself, but by the interaction between the magnetar's flare and the surrounding environment. Both theories remain active areas of research, and magnetars may not be responsible for all FRBs. Some fast radio bursts repeat regularly, producing multiple signals from the same location over time. Others appear only once and never repeat again. This suggests that multiple astrophysical mechanisms may be involved. Still, magnetars remain one of the leading explanations for at least a large fraction of these mysterious signals, and the implications are profound. Because fast radio bursts are so bright and travel such immense distances, they can serve as cosmic probes, tools that help astronomers study the structure of the universe itself. As FRB signals travel across billions of light-years, they pass through clouds of gas, galaxies, and intergalactic plasma. Each of these regions slightly alters the signal, leaving behind clues about the matter it encountered. By studying these signals carefully, astronomers can measure how much matter exists between galaxies. They can map the distribution of otherwise invisible intergalactic gas, and they can even test theories about the large-scale structure of the universe. In this way, magnetars, tiny objects only 20 kilometers wide, may help scientists study the entire cosmos. But magnetars are still mysterious in many ways. Some produce bursts frequently, while others remain quiet for long periods. Some emit radio waves, while others appear silent except for X-rays and gamma rays. Astronomers are still trying to understand why these differences occur. part of the challenge lies in the rarity of magnetars themselves. Only about 30 confirmed magnetars have been discovered within the Milky Way and nearby galaxies. Compared to the hundreds of billions of stars in our galaxy, this is an incredibly small population. Yet their influence is far larger than their numbers suggest. Magnetars demonstrate the incredible range of possibilities that stellar evolution can produce. From ordinary stars like our Sun to black holes that devour light itself, the universe is filled with objects that stretch the limits of physics. Magnetars stand near the extreme end of that spectrum. They are stars where magnetic energy dominates gravity, where quantum effects reshape the vacuum of space, where sudden eruptions can briefly outshine entire galaxies, and where signals born in violent magnetic storms can travel billions of light years before reaching our planet. But even magnetars have limits. Their immense magnetic fields cannot last forever. Over time, those fields decay, their violent eruptions become less frequent, and the once dangerous stars slowly fade into quiet neutron stars, drifting silently through space. Yet before that happens, magnetars may reveal one final secret, because in the most extreme magnetars, magnetic fields may reach strengths where even the structure of matter itself begins to change. And in the next part of our journey, we will explore the ultimate limits of magnetism, where fields become so powerful that atoms collapse, space becomes distorted, and the boundary between matter and energy begins to blur. Magnetars are not only violent stars, they are also the most powerful magnets known to exist anywhere in the universe. Their magnetic fields are so extreme that they push the laws of physics into territories rarely explored outside theoretical equations. To truly understand how extraordinary magnetars are, we need to consider the scale of their magnetism. Earth's magnetic field is gentle. It guides migrating birds, allows compasses to function, and protects our planet from the solar wind. Even the Sun's magnetic field, though capable of producing massive solar flares, is relatively weak compared to what exists inside a magnetar. A typical neutron star may have a magnetic field around 1 trillion Gauss. A magnetar can reach 1,000 trillion Gauss. That difference is enormous. If a magnetar were placed halfway between Earth and the Moon, its magnetic field would be strong enough to erase every credit card on Earth instantly. At a closer distance, it would disrupt electronics, distort atoms, and eventually pull molecules apart. But the true influence of such magnetic fields goes far beyond everyday objects. At magnetar level strength, magnetic forces begin competing with the fundamental forces that hold matter together. Atoms, which normally have roughly spherical electron clouds, begin to stretch and distort under the pressure of the magnetic field. Instead of round shapes, atoms become elongated structures aligned with the magnetic field lines. Imagine every atom turning into a tiny needle, pointing in the same direction. Chemical behavior under such conditions would be completely different from anything we observe on Earth. Molecules would bond differently. Materials would take on strange properties. Even the structure of solid matter would change. And on the surface of a magnetar, these effects dominate everything. The crust of a magnetar is not like the crust of Earth. It is composed of ultra-dense nuclear matter compressed under gravity billions of times stronger than anything on our planet. The atoms in this crust are squeezed together so tightly that electrons move freely between them, forming a kind of metallic lattice of atomic nuclei. But under the influence of the magnetars' enormous magnetic field, even this structure becomes distorted. Magnetic pressure pulls on the crust from multiple directions, constantly twisting and bending it. Over time, this pressure builds enormous stresses deep within the star's outer layers. Eventually, the crust fractures. These fractures release magnetic energy that has been building for years or even centuries. The result is a magnetar flare. Yet magnetars are not just powerful magnets. They are also enormous reservoirs of stored energy. The energy contained within a magnetar's magnetic field is staggering. Physicists estimate that a typical magnetar may store 10 to the power of 47 ergs of magnetic energy. For comparison, the total energy output of the Sun over its entire 10 billion year lifetime is about 10 to the power of 51 ergs. This means a single magnetar contains a significant fraction of the Sun's lifetime energy locked inside its magnetic field. When portions of that energy are suddenly released during magnetic reconnection events, the results can be explosive. Magnetic reconnection occurs when magnetic field lines that have been twisted together suddenly snap and reconnect in a new configuration. This process releases enormous amounts of stored magnetic energy, accelerating particles and producing intense radiation. On the Sun, magnetic reconnection causes solar flares. On magnetars, it creates eruptions millions of times more powerful. During a large magnetar flare, the star's magnetic field may reorganize itself on a global scale. The magnetosphere surrounding the star becomes filled with high-energy plasma, and powerful shockwaves ripple through space. These events release gamma rays, X-rays, and sometimes radio waves strong enough to be detected across vast cosmic distances. But the extreme magnetism of magnetars also leads to another remarkable phenomenon. It may affect the behavior of light itself. In classical physics, light is unaffected by magnetic fields. Photons carry no electric charge, so they should pass through magnetic fields without interaction. However, quantum electrodynamics predicts something different. Under extremely strong magnetic fields, like those near a magnetar, the vacuum of space becomes polarized. Virtual particles in the vacuum respond to the magnetic field, altering how light propagates through space. As a result, light traveling near a magnetar may become polarized in specific directions depending on the magnetic field structure. This effect means that even the empty vacuum surrounding a magnetar behaves like a physical medium. Astronomers are now searching for clear observational evidence of this effect by measuring the polarization of light emitted from magnetars. If confirmed, these observations would provide one of the most dramatic demonstrations of quantum physics occurring naturally in the universe. But magnetars may push physics even further. Some theories suggest that the strongest magnetars could approach the limit known as the Schwinger field, a threshold where magnetic fields become so strong that they can spontaneously create particles from empty space. At this level of intensity, the vacuum itself becomes unstable. Energy stored in the magnetic field can transform directly into pairs of electrons and positrons. Particles appear from nothing. These particles quickly annihilate or accelerate away from the magnetar, contributing to the energetic plasma environment surrounding the star. Although such effects remain difficult to observe directly, magnetars are one of the few places in the universe where these extreme processes might occur. They represent natural laboratories where the boundaries between classical physics and quantum physics begin to blur. Yet despite their incredible power, magnetars do not last forever. Their magnetic fields slowly decay over time. Unlike ordinary neutron stars that can remain stable for millions of years, magnetars are relatively short-lived objects. Their extreme magnetism gradually dissipates as energy is released through radiation and flares. Over tens of thousands of years, the magnetic field weakens. The violent eruptions become less frequent. Eventually, the magnetar transitions into a quieter state, indistinguishable from an ordinary neutron star. Its era of magnetic chaos comes to an end. But during its active lifetime, a magnetar may dramatically influence its surrounding environment. Powerful radiation bursts heat nearby gas clouds. Magnetic disturbances accelerate cosmic particles to extreme energies. Shockwaves from magnetar flares can propagate through surrounding space, altering the structure of nearby interstellar material. These stars may even help trigger the formation of new stars by compressing gas clouds in their vicinity. In this way, magnetars participate in the ongoing cycle of cosmic evolution. Massive stars collapse to form neutron stars. Some of those neutron stars become magnetars. Their violent activity shapes the surrounding galaxy, and eventually their energy fades, leaving behind quiet stellar remnants drifting through space. Yet magnetars still hold many mysteries. Astronomers continue discovering new examples, each with slightly different properties. Some produce frequent bursts. Others remain mostly silent. Some appear connected to fast radio bursts. Others behave like ordinary X-ray pulsars. The diversity of magnetar behavior suggests that there is still much to learn about these extraordinary objects. But one thing is certain: magnetars represent the most powerful magnets ever created by nature, and their existence reminds us that the universe is capable of producing environments far more extreme than anything we could ever replicate on Earth. Yet there is still one final question left to explore. Could a magnetar ever pose a real threat to Earth? And what would happen if one of these dangerous stars unleashed its power closer to our planet? In the next part, we will explore the potential dangers of magnetars and whether these cosmic giants could ever affect life on Earth. Magnetars are among the most powerful objects in the universe. Their magnetic fields are stronger than anything else known to exist, and their eruptions release enormous bursts of radiation capable of crossing entire galaxies. But this raises an unsettling question. What would happen if one of these dangerous stars were close to Earth? Could a magnetar actually threaten our planet? At first glance, the idea may sound like science fiction. After all, space is vast, and the nearest stars are trillions of kilometers away. Yet magnetars are real astrophysical objects scattered throughout the Milky Way. If one were to unleash a powerful flare nearby, the consequences could be significant. To understand the risk, we need to consider how magnetars release energy. The most dramatic events associated with magnetars are known as giant flares. These explosions occur when the magnetic field inside the star suddenly rearranges itself, releasing enormous amounts of stored magnetic energy. During such an eruption, a magnetar can release about 10 to the power of 46 ergs of energy in less than a second. That amount of energy is staggering. To put it into perspective, the Sun emits roughly 10 to the power of 33 ergs per second. A giant magnetar flare releases the equivalent of hundreds of thousands of years of solar energy in a fraction of a second. But distance matters. Because radiation spreads outward in all directions, its intensity decreases rapidly with distance. Even extremely powerful explosions become harmless if they occur far enough away. One of the most famous magnetar flares ever recorded happened on December 27, 2004. The source was a magnetar called SGR 1806-20, located about 50,000 light-years away, near the center of the Milky Way. When it erupted, the burst of gamma rays was so powerful that satellites orbiting Earth detected the signal instantly. Some instruments were temporarily overwhelmed by the intensity of the radiation. Yet despite its incredible power, the flare caused no harm to life on Earth. It was simply too far away. However, scientists studying the event realized something remarkable. Even from a distance of 50,000 light-years, the burst briefly disturbed Earth's upper atmosphere. The gamma rays ionized parts of the ionosphere, the region of charged particles high above our planet. The effect lasted only moments, but it proved that magnetar flares can influence planets across enormous distances. Now imagine the same flare happening much closer. If a giant magnetar flare occurred within about 10 light-years of Earth, the situation could be very different. At that distance, the gamma-ray radiation might interact strongly with Earth's atmosphere. High-energy photons could break apart molecules in the upper atmosphere, including ozone, which protects life from harmful ultraviolet radiation from the Sun. A significant depletion of the ozone layer could expose Earth's surface to increased levels of UV radiation. Such an event would not necessarily destroy life entirely, but it could disrupt ecosystems and cause widespread biological damage. Fortunately, the chances of this happening are extremely small. Astronomers have carefully mapped nearby stars within about 100 light-years of Earth. None of them appear capable of becoming magnetars. Magnetars form only from extremely massive stars far larger than our Sun, and there are no such stars close enough to pose a threat. In fact, most magnetars in the Milky Way are located thousands or tens of thousands of light-years away, typically near regions where massive stars are born. This means that although magnetars are dangerous objects, the nearest ones are safely distant. But magnetars could influence Earth in another way. When magnetars erupt, they sometimes produce bursts of cosmic rays, high-energy particles accelerated by magnetic fields. These particles travel through space at nearly the speed of light. If enough of them reached Earth, they could interact with our atmosphere and produce showers of secondary particles. Normally, Earth's magnetic field and atmosphere shield us from most cosmic radiation, but an extremely intense nearby event could temporarily increase radiation levels in the upper atmosphere. Again, however, the distance between Earth and known magnetars makes this scenario highly unlikely. Still, studying these potential effects helps scientists understand how cosmic events influence planetary environments. In fact, some researchers believe that past mass extinctions on Earth may have been influenced by astrophysical events such as nearby supernova explosions or gamma-ray bursts. Magnetar flares belong to the same category of extremely energetic cosmic phenomena, yet magnetars may also affect the universe in more subtle ways. Their powerful magnetic fields accelerate particles to extremely high energies. These particles contribute to the population of cosmic rays traveling through the galaxy. Some of these cosmic rays eventually reach Earth, where they collide with molecules in our atmosphere. These collisions create cascades of secondary particles that scientists can detect using ground-based observatories. By studying these cosmic rays, researchers gain insights into some of the most energetic processes in the universe, including magnetar flares. Magnetars may also help shape their local environments. When a magnetar erupts, the blast of radiation can heat nearby gas clouds. The sudden burst of energy may compress surrounding material, triggering shockwaves that propagate through the interstellar medium. In some cases, these shockwaves may even help initiate the formation of new stars. This means magnetars are not just destructive objects. They are also participants in the cycle of stellar evolution. Massive stars explode as supernovae, leaving behind neutron stars. Some neutron stars become magnetars. Magnetars release energy into their surroundings, and that energy may help create the next generation of stars. In this way, magnetars contribute to the ongoing transformation of matter throughout the galaxy. Yet despite their immense power, magnetars are relatively short-lived compared to other stars. Their intense magnetic fields slowly decay over time. As the field weakens, the violent eruptions become less frequent. After about 10,000 to 100,000 years, the magnetar's magnetic energy has largely dissipated. The once dangerous star becomes a quiet neutron star. Its violent youth is over. But during that brief active period, magnetars represent one of the most extreme environments in the universe. They are stars where magnetism dominates gravity, where atomic structures collapse under magnetic pressure, where bursts of energy can travel across entire galaxies, and where the laws of physics are pushed to their limits. But even magnetars are not the final word in cosmic power. There are events in the universe even more energetic than magnetar flares, events capable of outshining entire galaxies. And in the next part of our journey, we will explore how magnetars may be connected to some of the most mysterious and powerful signals ever detected from deep space. Signals that travel billions of light years before reaching Earth. Signals that may reveal hidden processes shaping the universe itself. Despite their terrifying power, magnetars are not eternal. Like all stars, they are temporary objects in the long history of the universe. Their reign of magnetic violence lasts only a brief moment on cosmic timescales. Eventually, even the most dangerous stars begin to fade. The story of a magnetar's end is not marked by a sudden explosion or collapse. Instead, it is a slow transformation, a gradual weakening of the very force that defines it, its magnetic field. At the moment of its birth, A magnetar possesses one of the strongest magnetic fields ever created in nature. These fields can exceed 10 to the 15th power Gauss, a strength that overwhelms nearly every other force acting on the star. The magnetic field twists the star's crust, powers violent flares, and fills the surrounding space with intense radiation. But maintaining such an enormous field requires energy. Over time, that energy slowly leaks away. Every flare, every burst of radiation, every rearrangement of magnetic field lines drains a small fraction of the magnetar's stored magnetic energy. The process is gradual, but it is relentless. The magnetar begins to weaken. Astronomers believe that the active lifetime of a magnetar typically lasts between 10,000 and 100,000 years. Compared to the billions of years that ordinary stars can survive, this is extremely short. In cosmic terms, magnetars live fast and die young. During their early years, magnetars are extremely active. Their crust fractures frequently under the stress of their twisting magnetic fields. Each fracture releases bursts of X-rays and gamma rays. Observatories in space regularly detect these signals, allowing astronomers to track magnetar activity across the galaxy. But as centuries pass, the star gradually becomes quieter. The magnetic field begins to decay. This process is driven by several mechanisms inside the neutron star. One important factor is the motion of charged particles within the star's interior. Even though the matter inside a neutron star is incredibly dense, small movements of electrons and protons can slowly dissipate magnetic energy. Another process is known as Hall drift. Inside the crust of the magnetar, electric currents flow through the dense lattice of atomic nuclei. These currents interact with the magnetic field, slowly rearranging its structure over time. As the field shifts and evolves, it gradually weakens. There is also a phenomenon called ohmic decay. In this process, electrical resistance inside the star's crust converts magnetic energy into heat. This heat warms the surface of the neutron star, causing it to emit X-rays. Over thousands of years, this heating gradually releases the energy stored in the magnetic field. Together, these processes slowly drain the magnetar's magnetic strength. As the field weakens, the violent stresses on the crust diminish. Starquakes become less frequent. Gamma ray flares become rarer. Eventually, the magnetar enters a calmer stage of its life. At this point, the star may still emit X-rays due to the residual heat generated by magnetic decay. But the dramatic bursts that once made it one of the most dangerous objects in the galaxy begin to fade away. After tens of thousands of years, the magnetar's magnetic field may weaken to the point where it becomes indistinguishable from that of an ordinary neutron star. The magnetar is effectively gone. All that remains is a dense stellar corpse, an object still incredibly compact and massive, but no longer dominated by overwhelming magnetism. This quiet remnant may continue existing for millions or even billions of years, drifting through the galaxy, invisible, silent. Yet even after magnetars fade, they may leave behind traces of their former power. The regions surrounding magnetars often contain supernova remnants, expanding clouds of gas and dust created when the massive star that formed the magnetar exploded. These remnants can persist for tens of thousands of years, glowing faintly in X-rays and radio waves. Inside these remnants, astronomers sometimes find the neutron star left behind by the explosion. If the star is still young enough, it may still display magnetar-like activity. But if enough time has passed, the once dangerous magnetar may have already transformed into an ordinary neutron star. This raises an interesting possibility. Some neutron stars we observe today may actually be ancient magnetars whose magnetic fields have long since faded, their violent past hidden by time. Astronomers are still trying to determine how common this transformation might be. If magnetars frequently evolve into normal neutron stars, then many neutron stars across the galaxy could be the quiet descendants of these once powerful objects. This idea helps explain the diversity observed among neutron stars. Some neutron stars behave as pulsars, emitting beams of radiation as they spin rapidly. Others appear as quiet X-ray sources. And some, like magnetars, release sudden bursts of energy due to magnetic instabilities. These different behaviors may represent different stages in the life cycle of neutron stars. A young neutron star may begin as a magnetar. Over time, as its magnetic field decays, it transitions into a quieter state. Eventually, it may become an ordinary neutron star, slowly cooling in the darkness of space. But magnetars may also leave behind another legacy. During their active lifetimes, they release enormous amounts of energy into their surroundings. This energy can influence nearby gas clouds, accelerating particles and altering the structure of the interstellar medium. In some cases, magnetar activity may even help trigger the collapse of nearby gas clouds, leading to the formation of new stars. If this happens, the death of one massive star may indirectly contribute to the birth of many others. This cosmic recycling process lies at the heart of galactic evolution. Stars form, stars die, their remnants reshape the surrounding environment, and new stars emerge from the debris. Magnetars are part of this grand cycle. They represent one of the most extreme phases in the life of a massive star, a phase where magnetic energy dominates everything. Yet even as magnetars fade, scientists continue to study them with growing interest. New telescopes are being developed to detect the subtle signals that these stars produce. X-ray observatories, gamma-ray detectors, and radio telescopes all contribute to our understanding of these objects. Some of the most exciting discoveries about magnetars have occurred only in the past 2 decades, and many mysteries remain. For example, astronomers are still unsure exactly why some neutron stars become magnetars while others do not. They are also trying to understand why some magnetars produce fast radio bursts, while others remain radio silent. And there is still much to learn about how magnetic fields evolve inside neutron stars over time. Each new observation provides clues. Each flare detected by a telescope adds another piece to the puzzle. But magnetars may also help answer even deeper questions about the universe, because by studying these extreme stars, scientists can test theories about quantum physics, nuclear matter, and the behavior of space itself under extreme conditions. Magnetars push the laws of physics to their limits, and in doing so, they reveal how the universe behaves when pushed to its most extreme states. Yet even with everything we have learned about magnetars, one final mystery remains. How many of these dangerous stars exist in our galaxy? And could there be magnetars hidden nearby, waiting to reveal themselves through sudden bursts of radiation? In the final part of our journey, we will explore how astronomers search for these elusive objects and what their discoveries might reveal about the hidden population of magnetars scattered across the Milky Way. For many years after their discovery, magnetars were thought to be incredibly rare objects. Astronomers knew of only a handful scattered across the galaxy, each revealed through bursts of gamma rays or powerful X-ray emissions. Compared to the hundreds of billions of stars in the Milky Way, magnetars seemed almost non-existent. But as telescopes became more sensitive, a new realization began to emerge. Magnetars might be far more common than we once believed. The challenge is that magnetars are difficult to detect. Unlike ordinary stars, they do not shine brightly in visible light. Their small size and immense density mean that most of their energy is released in X-rays and gamma rays, wavelengths that require specialized space telescopes to observe. From Earth's surface, our atmosphere blocks these high-energy forms of radiation. That protection keeps us safe, but it also hides many magnetars from view. To find them, astronomers must rely on instruments placed above the atmosphere. Satellites such as NASA's Chandra X-ray Observatory, XMM Newton, and the Fermi Gamma Ray Space Telescope continuously scan the sky for bursts of high-energy radiation. Sometimes they detect sudden flashes lasting only fractions of a second. These brief signals are often the first clue that a magnetar exists somewhere in that region of space. Once a burst is detected, astronomers search for its source. If repeated bursts appear from the same location, scientists begin investigating more carefully. X-ray telescopes may then observe a faint but persistent glow, evidence of a neutron star whose magnetic field is slowly releasing energy. Over time, patterns emerge. Some magnetars produce clusters of bursts over a few days or weeks, then fall silent for years. Others release only occasional flares, making them extremely difficult to identify. Because of this unpredictable behavior, many magnetars likely remain hidden. Current estimates suggest that the Milky Way may contain several hundred magnetars, even though only about 30 have been confirmed so far. Most of them may simply be too quiet or too distant for us to detect with current technology. Some may lie buried within thick clouds of interstellar dust near the center of the galaxy, where visible light cannot penetrate. Others may have already aged beyond their most active phase, becoming quiet neutron stars whose magnetic fields have partially decayed. But astronomers are developing new techniques to uncover these hidden objects. One promising approach involves studying supernova remnants. Every magnetar begins its life in a violent stellar explosion. When a massive star collapses, the outer layers of the star are blasted outward into space, forming a glowing shell of gas and debris. This expanding cloud can remain visible for tens of thousands of years. If astronomers detect a neutron star at the center of a supernova remnant, they may study its properties carefully to determine whether it could be a magnetar. Another method involves searching for unusual X-ray pulsations. Neutron stars often spin rapidly, producing beams of radiation that sweep across space like the beam of a lighthouse. If the beam points toward Earth during each rotation, astronomers detect regular pulses of radiation. Magnetars sometimes behave like pulsars, but their pulses often display unusual patterns due to their complex magnetic fields. By analyzing these signals, astronomers can identify candidates that may be magnetars. radio telescopes also play an increasingly important role. Although magnetars were once thought to be silent at radio wavelengths, several have now been observed producing radio pulses. These signals can reveal details about the star's rotation and magnetic field structure. In recent years, radio observations have even linked magnetars to fast radio bursts, strengthening the connection between these mysterious signals and the universe's most powerful magnets. The discovery of radio-emitting magnetars opened an entirely new window into their behavior. It also suggested that magnetars may evolve through multiple stages during their lifetimes. Some may begin as extremely active X-ray sources, then transition into radio-emitting pulsars as their magnetic fields slowly decay. Others may follow completely different evolutionary paths. Astronomers are still trying to understand these transitions. Another exciting development involves the detection of transient magnetars. Unlike traditional magnetars that emit persistent X-ray radiation, transient magnetars remain almost completely invisible for long periods of time. Then, suddenly, they erupt into activity, producing bursts of radiation that make them briefly detectable. After the burst phase ends, the magnetar fades back into obscurity. These transient objects suggest that the galaxy may contain many magnetars that are currently dormant. They simply haven't erupted yet. This possibility has led astronomers to speculate that the Milky Way may host far more magnetars than we currently observe. Some could be lurking in quiet regions of space, waiting for a sudden starquake to reveal their presence. Others may already have transitioned into ordinary neutron stars whose violent past is now hidden. Understanding how many magnetars exist in the galaxy is important for several reasons. First, magnetars influence their surrounding environments. Their bursts of radiation heat nearby gas clouds and accelerate particles to extremely high energies. These processes contribute to the complex ecosystem of the interstellar medium. Second, magnetars help scientists study extreme physics. Their intense magnetic fields allow researchers to test theories about quantum mechanics, nuclear matter, and electromagnetic forces under conditions that cannot be recreated in laboratories on Earth. And third, magnetars may play a key role in producing fast radio bursts, signals that can travel across billions of light years. By identifying more magnetars, astronomers can better understand how these mysterious signals are generated. But finding these hidden stars requires new technology. Future observatories may dramatically expand our ability to detect magnetars. One such project is the Square Kilometre Array, SKA, a massive radio telescope currently under construction. When completed, it will be one of the most sensitive radio observatories ever built. The SKA may detect faint radio signals from neutron stars across much of the Milky Way, potentially revealing many previously unknown magnetars. Other missions, such as next-generation X-ray telescopes, will search the sky for bursts of high-energy radiation with unprecedented sensitivity. These instruments could discover magnetars in distant galaxies or detect rare flares from magnetars hidden within our own. As technology improves, our catalogue of magnetars will likely grow. Each new discovery will add to our understanding of these extraordinary stars. But even as we search for more magnetars, one profound truth remains clear. These objects represent one of the most extreme outcomes of stellar evolution. They are the remnants of massive stars that lived fast and died violently. They contain magnetic fields so strong that they reshape atoms and influence the vacuum of space. And they unleash bursts of energy capable of crossing entire galaxies. Yet despite all this power, magnetars are ultimately fragile. Their magnetic fields slowly fade. Their eruptions become less frequent, and eventually their violent youth ends. But before they disappear into quiet neutron stars, magnetars leave behind a remarkable legacy. They show us just how extreme the universe can become. And in the final part of our journey, we will step back and reflect on what magnetars reveal about the limits of nature itself, how these strange stars push the boundaries of physics, and what they teach us about the hidden forces shaping the cosmos. Across the universe, stars are born, live their lives, and eventually die. Some fade quietly into white dwarfs, others collapse into black holes, but a small number follow a far more extreme path. They become magnetars, the most dangerous stars known to exist. These objects represent the ultimate expression of magnetic power in nature. A magnetar is not large. In fact, it is surprisingly small. The entire star measures only about 20 kilometers across, roughly the size of a city. Yet inside that tiny sphere lies a mass greater than our sun, compressed into one of the densest forms of matter in the universe. But it is not gravity that defines a magnetar. It is magnetism. The magnetic fields of these stars are so powerful that they dominate everything around them. At strengths exceeding a quadrillion times Earth's magnetic field, magnetars push the limits of what physics can describe. Their fields twist the star's crust, reshape atoms, and influence the behavior of space itself. Nowhere else in the universe do we find magnetism so extreme. Yet magnetars are born from a familiar cosmic process, the death of massive stars. When a star many times larger than our sun reaches the end of its life, its core collapses in a violent supernova explosion. The outer layers of the star are blasted into space, leaving behind a dense neutron star. Sometimes, under the right conditions, that newborn neutron star emerges spinning rapidly with an enormously amplified magnetic field. A magnetar is born. For thousands of years after its creation, the magnetar lives in a state of constant tension. Its magnetic field twists and coils deep within the star, slowly building enormous stresses in the crust. Eventually, the crust fractures in violent starquakes. Each fracture releases bursts of radiation that travel across the galaxy. Gamma rays, X-rays, and sometimes powerful radio waves. These eruptions can be so energetic that they briefly outshine every other X-ray source in the Milky Way. Yet these bursts represent only a fraction of the magnetar's power. Occasionally, the magnetic field rearranges itself in a massive event known as a giant flare. During these rare eruptions, the magnetar releases enormous amounts of energy in less than a second, enough to rival the total output of the sun over hundreds of thousands of years. One such event occurred in December 2004, when the magnetar SGR-1806-2 unleashed the most powerful flare ever recorded in our galaxy. Even though the star was located 50,000 light-years away, the radiation briefly disturbed Earth's atmosphere. It was a reminder that events occurring across the galaxy can still leave detectable fingerprints here on our planet. But magnetars are not only destructive objects, they are also extraordinary laboratories for studying the fundamental laws of physics. The extreme conditions around magnetars allow scientists to observe phenomena that cannot be recreated anywhere else. Their magnetic fields may influence the vacuum of space itself, causing strange quantum effects such as vacuum birefringence, where light behaves differently depending on its orientation within a magnetic field. In these environments, even the emptiness of space becomes altered. Magnetars also reveal how matter behaves under unimaginable pressure and density. Inside these stars, atomic nuclei are crushed together into exotic states of matter that challenge our understanding of nuclear physics. By studying magnetars, astronomers gain insights into some of the most extreme forms of matter that exist anywhere in the universe. But magnetars do not remain powerful forever. Over time, their magnetic fields slowly decay. Every flare, every burst of radiation releases a small fraction of the energy stored within the star's magnetic field. Gradually, over tens of thousands of years, the field weakens. The violent eruptions become less frequent. The magnetar begins to quiet. Eventually, the once dangerous star transitions into an ordinary neutron star. Its magnetic storms fade, its eruptions cease, and it drifts silently through space, another stellar remnant among billions of others scattered throughout the galaxy. Yet during its brief active lifetime, a magnetar leaves a lasting imprint on the universe. Its eruptions heat nearby gas clouds. Its magnetic disturbances accelerate cosmic particles. Its bursts of radiation can travel across galaxies. And in some cases, magnetars may even generate mysterious signals known as fast radio bursts, brief flashes of energy detected billions of light years away. These signals have puzzled astronomers for years, but recent discoveries suggest that magnetars may be responsible for at least some of them. If this connection is confirmed, it would mean that magnetars are not only dangerous stars within our galaxy, they are also cosmic beacons visible across the universe. Even though magnetars are rare, their influence extends far beyond their small numbers. They represent the extremes of stellar evolution. They push physics to its limits, and they reveal how powerful the forces of nature can become under the right conditions. Yet perhaps the most remarkable thing about magnetars is how small they are. An object only 20 kilometers wide can unleash explosions capable of affecting planets across thousands of light years. A star the size of a city can contain enough magnetic energy to rival the power of entire stellar systems. In the vast scale of the cosmos, magnetars remind us that size is not always what determines power. Sometimes the most dangerous objects are also the most compact. And somewhere out there in the Milky Way, hidden among billions of stars, these dangerous magnets continue to twist, crack, and erupt, silent reminders that the universe is capable of producing forces far beyond anything we experience here on Earth. Magnetars may be rare, but when they awaken, the universe notices.